As we know, electric motors are used in many applications from electric vehicles, electric bikes, and drones, among other applications. And in this video and the coming ones or following ones, we are going to learn how to design the electronic drivers for brushed DC motors. The first thing, in order to be able to design the electronic driver of a DC motor, we need to find the equivalent circuit of a DC motor. And what we're going to find out is that the equivalent circuit of a DC motor, essentially it has an equivalent series resistor RA, where A is abbreviation for armature, and equivalent series inductance LA, and internal voltage source EB, which is called back electromotive force. And then we have the two terminals of the motor across which we apply voltage. In this particular video, we're going to see or find the torque produced by the motor as a function of the current flowing into the motor or armature. Also, we're going to see the origin of the back electromotive force. So first of all, an electric motor is basically a torque transducer. By that, I mean it takes in electric power, a DC motor or a motor essentially generally takes in electric power and convert it into an equivalent amount of mechanical power, of course assuming lossless operations, as the motor is essentially lossless. So what's electric power? Well, the electric power, as we know, is a product of voltage and current. The voltage applied across the motor times the current going into the motor. What about the mechanical power, the produced mechanical power? Well, the mechanical power is a product of the torque produced by the motor times its angular velocity. We know that power is measured in watt. Torque in this case will be measured in Newton meter, and angular velocity will be measured in radians per second. Now let's see what are the basic components of a brushed DC motor. Well, the first component, if we look at this simple toy DC motor, brushed DC motor, we have the housing, and within this housing we have two permanent magnets, say north and south. So all of this is called the stator. And of course the two permanent magnets, their function is to produce magnetic field. And then inside these two magnets we have the rotor. And the rotor basically, it contains iron core, and within this iron core we have coils, what we call armature. Armature is just a short word for a rotating coil. And then within the rotor we have these two copper pieces. The whole idea is we need to provide voltage across the coil or armature, right? That's inside the iron core. And to reach power or voltage and current to these coils, essentially we need to reach the two terminals of the coil. So we connect the two terminals of the coil to two pieces of copper that we call, or that are called, commutator. And then this commutator, we provide the power from these two terminals. need to touch or essentially get connected to the external world through these two terminals. So we have, through these two terminals, we have two copper pieces, or what we call brushes or carbon brushes. And these carbon brushes essentially get connected to the commutator, these two copper pieces, as the rotor is rotating, providing the external power to the coil essentially, or the armature. Now, let's see how the motor produces torque. Here I'm showing a side view of the motor. So essentially, if we look at the rotor from here. So first of all, let's see the magnetic force. If we have two permanent magnets like that, and we have a piece of copper here, and somehow we reach it or connect it to a voltage source, what will happen? Current is going to flow. And of course we have the magnetic field from north to south. So within this wire, since it's carrying current and it's placed into magnetic field, what will happen, essentially we'll find it moving out of the power point slide according to the right hand rule. And it moved out of the power point slide due to a force that's directed out of the slide. And this magnetic force is equal to the strength of the magnetic field produced by the permanent magnets times the value of the current times the length of the wire. Okay. So similarly, what happens is, this is the rotor, the commutator. This part is the commutators, or the commutators, these two copper pieces. And these two copper pieces connects to the external world via the brushes, or basically the carbon brushes. And if we apply a DC voltage source, essentially current is going to flow into the armature. So it will go to the this commutator, the left one, and then it will flow into the armature, and then it will go into the power point slide. So if we look at the top view, so essentially current is going to flow clockwise into the armature, and then it will come back from here and then back to the battery that we are applying across the armature. And again, here we have magnetic field between the north and south magnets, and we have current flowing into a wire. So essentially we'll find that according to the right hand rule, the left wire, this piece, the left wire will have a force that's applied across it or on it that's pointing downward, and the right wire or piece of wire from the coil essentially will have a force applied across on it pointing upward. And as you can expect, when we have two forces opposite with a distance between them, essentially we'll get torque. And this torque will be equal to Fm times the produced magnetic force times the distance between the two forces. The magnetic force is essentially equal to the strength of the magnetic field produced between the north and south by the amount of current flowing into the armature and the length of the wires. Since we have, if we look from the top, we'll have the armature, so this length essentially. Let's take this length equal to B length, and then we have the distance between the two opposite forces. So this distance Well, if we look at this triangle and assume this angle is phi, then this distance is equal to b times sine phi. Where phi is essentially the displacement or the angular displacement of the rotor or the armature from the vertical position. So this angle. Now, as you can see, the rotor here, or sorry, the armature here has multiple turns. So each turn will produce the same amount of torque, so essentially we'll multiply by n. And then if we assume that the motor is rotating counterclockwise, of course this force is downwards, this one upwards, so the motor will rotate counter or move counterclockwise in this case, or in this example. If we assume that the under steady state or the armature is rotating under steady state, so essentially its angular speed or angular velocity is going to be constant. So the phase shift or this phase essentially phi of the rotor with respect to the vertical position will be its angular velocity times time t. And so we can replace phi in the torque expression by nb ia length times b times sine omega m t. Another simplification or modification to the equation we can do, length times b, that's the internal area of the armature, length times b. So we can replace it by a, the internal area of the armature, and then a multiplied by the produced magnetic field of the permanent magnets. We can replace it by flux, or has the units of flux. And that's basically the expression for the torque that's produced by the electric motor or the brushed DC motor. So it will depend on the strength of the permanent magnets. It will also depend on the area, essentially, that's inside the armature. The larger the armature, the larger the torque, which makes sense. Larger motors are able to produce larger amount of torque and larger amount of mechanical power. It will also be proportional to the current that's flowing into the armature. And finally, it's function of time. So how does it look like versus time? Well, let's assume this is basically the armature and this is just a reference point. In this position, the angle phi is equal to 0. Then it rotates counterclockwise. It comes at phi equal to pi over 2 or 90 degrees. Then essentially we'll have the this point coming at 180 degrees. So during all that, the torque, we found that it's proportional to sine phi, right, is angular position, whereas this is omega mt or phi essentially. So between 0 and pi, essentially the torque follows a sine function, very sinusoidally, and its maximum value will be basically at pi over 2 or in this position, and later on also at 3 pi over 2. Now if we look at the commutator, these two rings essentially, let's sketch them here, and this makes the upper one thick and the bottom one thinner. So in the horizontal position, what happened is essentially, since the brush is thick, is going to short both rings of the commutator, and essentially the voltage applied across the rotor is 0. okay, and there is no force, but essentially due to inertia the rotor will continue to rotate. Now when it's at 90 degrees, we have the thick ring at the left, the thin one on the right, and of course we have the brushes touching or connecting them to the external wall. Now at 180 degrees we have the thick ring here, thin at the bottom at south, and the thin one at the top. And then let me continue at the bottom here, at phi equal to 3 pi over 2. So this is the reference point, and then it comes at 3 pi over 2. So we have the thick ring on the right and the thin one on the left. You see, if we compare between phi equal to pi over 2 scenario and phi equal to 3 pi over 2, the thick ring is on the left when we are at pi over 2 position. When we are at 3 pi over 2 position, the thick ring is going to be on the right side. So what will happen here at pi over 2, essentially the positive terminal of the battery is touching the thick ring, while at 3 pi over 2 the negative terminal of the battery is touching the thick ring. So that's why it's called commutator. Essentially it flipped the voltage that's applied across the armature every 180 degree angle. And when you reverse that, essentially the current flowing into the armature is going to flip as well. And so the torque will be or continue essentially in the same direction. So note that the voltage here is flowing, the current here is flowing from right to left during the first 0 to pi, first half cycle. And similarly, in the other half cycle, still the current is flowing from right to left. Okay? And so the torque will always be in the same direction. All right, now let's see, the second point is what about the source of the EB in the model of the motors that we're going to see. We said we have equivalent series resistance of the armature, the equivalent series inductance of the armature, and then we have an internal voltage source. What is the source or the cause of this internal voltage source? Well, first of all, this internal voltage source is called back electromotive force. We know at the end of the day, if we have a coil, and this coil we put between two magnets, and we rotate it around an axis, say counterclockwise or clockwise, and we rotate it, say, using a handle, for example. We know that what we'll see output power, right? It will act as a generator. That's essentially what the generator does. You have an armature, and then you rotate it, say, using waterfall or another source of force or torque, and essentially it's going to produce electricity or voltage and power. So the same thing will happen since this armature is rotating with an angular velocity equal to omega m within magnetic field between the north and south magnets. What will happen is the armature is going to produce electromotive force, or essentially back voltage, essentially. You can say it simply. And this back voltage, you will find that if we follow Faraday's law of induction, is such that it produces the produced voltage is in the same direction as applied DC voltage. So if we look here in this simple model, if this is the DC voltage applied across the motor, what will happen is the generated back electromotive force, or essential internal voltage, due to the rotation of the armature within the magnetic field produced by the permanent magnets, is such that the positive in the same alignment as the applied positive and negative in the same direction. And why is that? So let me sketch. So we have two cases. The produced internal voltage can be this polarity, or so we have two cases, either this polarity or the second polarity at the bottom. And if we follow Faraday's law, we'll find that the internal voltage or back electromotive force is following scenario 2. The polarity is positive at the top and negative at the bottom. Why? Well, essentially it's trying this voltage, if we do KVL around this loop, essentially the current here is going to be reduced, because now it's the difference, the voltage across these two elements will be the difference between the applied voltage and the generated internal voltage or electromotive force generated by the rotation of the armature inside the magnetic field of the motor, right? So the back EMF, that's why it's called back, essentially is trying to fight the applied voltage, reduce the amount of current that's flowing into the armature, and thereby reduce the produced torque. On the other hand, if it was generated in this way, it's essentially is trying to increase the current flowing into the rotor and thereby increasing the torque. And in transient response, it's trying to increase the angular velocity of the rotor or armature, and therefore when you increase the angular velocity, will increase again EB, and EB increases, so you get into a positive feedback system that's unstable, and essentially the torque will keep increasing, the angular velocity will keep increasing, the EB will keep increasing until, like, that doesn't make sense essentially. On the other hand, we have the produced back electromotive force due to the rotation of the armature inside the magnetic field of the motor is opposing the applied voltage, essentially we have a stable model. And of course, all that is very simple. You can just apply Faraday's law and you will see that the generated back voltage or back electromotive force is opposing the applied voltage VDC in the case of an electric motor. So basically it's trying to reduce the current that's produced into the armature and thereby reduce the torque produced by the motor. But of course it will reach steady state. Now, if we look at the back electromotive force, and remember here the example of a generator. If we have an electric generator, and essentially there is a handle here, and this handle, we are rotating this handle. So we can expect that the amount of voltage that's produced and power that's produced by the electric generator will be proportional to the rotation speed that essentially we apply to the generator. It will also be proportional to the number of turns of the armature inside the generator. It will also be proportional to the permanent magnets of the generator. And it will also be proportional to the area of the armature, area inside, or the size essentially of the armature. So it will be essentially proportional to the product of L, length times width essentially of the armature. The larger the size of the generator, the more electricity that will be generated, so essentially proportional to this area. But due to the rotation of the rotor, whether it's inside the generator or electric motor, the area that's crossed, or the flux essentially inside the rotor changes with time, right? Depending on the position of the rotor inside the motor, right? If it's in the vertical position, we have the maximum amount of flux going through the rotor. On the other hand, if it's a horizontal, zero flux is linking through the area inside the rotor. And so it was going to be a function of time, and if we follow Faraday's law, we'll find it essentially proportional to sine omega mt. So we can see that EB is going to be equal to omega m. We have n number of turns times b times a sine omega m t, to signify that the essentially the generated back voltage or back electromotive force changes with time, as well as the torque or what's happening to torque. And again, BA essentially we can call it, let's take n outside, so n, we have phi f, the flux, the maximum flux going through the armature. Then we have omega m, then sine omega mt. So that's the value of the back electromotive force or back voltage that is generated due to rotating the armature within constant magnetic field. Okay, so we apply voltage externally. The rotor essentially is going to start rotation, or the armature is going to rotate counterclockwise, and as it's rotating and gaining speed, so omega m is increasing, we'll find that EB, the back EMF, is also increasing, and eventually we'll find that omega m, or the angular velocity, is going to reach a steady state value versus time. Okay.